Welcome to Numerical Methods for Scientists and Engineers. Matrix inversion with Gauss-Jordan Method. The inverse of a matrix A, denoted as a to the power of -1, is defined as a matrix that, when multiplied by A, regardless of which side it is multiplied, results in the identity matrix. There are other methods that work for small matrices, say, n less than 5. However, the Gauss-Jordan method can be efficiently used to find the inverse of a matrix of any size. Not all matrices have an inverse. A matrix A is invertible or non-singular if it is a square matrix and its determinant is non-zero. In this method, first, the augmented matrix, consisting of matrix A and the identity matrix, is set up. Then the augmented matrix is transformed into its reduced row echelon form, which, for an invertible matrix, is the identity matrix. This transformation is simultaneously applied the identity matrix, which at the end results in the inverse of A. Let's break the steps down for a 4 by 4 matrix. The augmented matrix is set up as a rectangular matrix with A on the left and I on the right side. The goal is to systematically apply a series of elementary row operations, scaling, pivoting, or elimination, to transform the augmented matrix to move the identity matrix to the left, as illustrated. The matrix on the right of the identity matrix is the inverse. Keep in mind that the symbols used as matrix elements in these illustrations do not represent the same numerical value, and some of which may even be 0. The goal is to transform the matrix A on the left-hand side into the identity matrix. This is done systematically. That is, the identity matrix is, so to speak, moved to the left column by column using row operations. In the first pass, the first column of the identity matrix is moved. Through row operations, the second column of the identity matrix is created in the second pass. Meanwhile, as you noticed, the row operations altered the first and second columns of the identity matrix on the right side. In the third pass, the third column of the identity matrix is created, while the third column of the identity matrix is altered. Finally, the fourth column of the identity matrix is moved in the fourth pass. The identity matrix on the right is altered to a completely different matrix, which is now the inverse of the matrix A. Now let us consider a numerical example. This 4 by 4 matrix is non-singular and has an inverse. We set up the augmented matrix as follows, where matrix A is on the left, and the identity matrix is on the right side. The goal of the first pass is to create the first column on the identity matrix through row operations. Since the row operations are applied to a row as a whole, naturally the fifth column elements will also be altered. The augmented matrix for this example is as shown. We can create the pivot in the first row equal to 1 by adding the fourth row to the first row. So first row and plus fourth row gives the original first row, the pivot, is replaced as a result of this row operation. Now we want to create zeros below 1 in the first column. First, we use the first row to eliminate the -12 in the second row. To accomplish that, 12 times the first row is added to the second row. Row 2. 12 times row 1 yields The original second row is replaced with the new row obtained as a result of this row operation. Next, we use the first row to eliminate the -5 in the third row. 5 times the first row is added to the third row, which gives the following row. This row, obtained as a result of the row operation, replaces the third row. Next, we use the first row to eliminate the 16 in the last row. To achieve this, -16 times the first row is added to the last row. Which gives the following. The new row replaces the fourth row, which marks the end of first pass. The goal of the second pass is to create the second column on the identity matrix via row operations, which also alter the sixth column elements. Notice that, here, we can create a 1 in the last row by adding 3 times row 3 to row 4. In the last row, we get a 1. However, we would have liked it to be in the second row. But that's okay. Once we've eliminated the second column, we can swap the second and fourth rows. This is something that we do when using hand calculation. Computer algorithms in general would use scaling of the second row to get a 1. Next, to eliminate the 3 in the third row, we use the pivot, that is, the last row. To do that, we add -3 times the fourth row to the third row. The new computed row obtained replaces the third row. To eliminate the 6 in the second row, we use the fourth row, acting as the pivot. -6 times the fourth row is added to the second row, which gives. Then the second row is replaced by the computed row. Then we use the last row to eliminate the -1 in the first row, by adding the fourth row to the first row as follows, which gives. The first row is then replaced by the newly computed row. As the last step of the second pass, we interchange the second and fourth rows. This marks the end of second pass. The third pass goal is to create the third column of the identity matrix in the augmented matrix via row operations. This process will alter the seventh column. Note that there are 2 zeros already in the third column. We only need to create a 0 in the last row. But it is worth noting that general-purpose Gauss-Jacobi codes perform elementary operations without checking whether the elements consist of zeros. At this step, first we multiply the third row with -1 to create the pivot. Next, we use the third row to eliminate the -2 in the last row. So we add 2 times the third row to the last row, which gives. The last row is replaced by the row obtained as a result of the elimination operation. The fourth pass goal is to create the fourth column of the identity matrix through row operations. This process alters the last column. Here, the last row of the fourth column is already 1. So there is no need to scale this element. We use the last row, the pivot, to eliminate the -3 in the third row. 3 times the fourth row is added to the third row as follows, which gives. The third row is replaced by the new row obtained. We use the pivot, the last row, to eliminate the -2 in the second row. 2 times the fourth row is added to the second row, which gives. Then the new row obtained replaces the third row. Finally, we use the last row to eliminate the -1 in the first row. To achieve this, the fourth row is added to the first row, which gives. and this last row replaces the first row. This marks the end of Gauss-Jacobi algorithm. Here, we have obtained the identity matrix on the left side of the augmented matrix. The right side of the augmented matrix is the matrix inverse. That is all for now. See you next time with another topic. Bye.